Okay, good. Let me introduce this session. I hope that everybody can join because maybe some other sessions are a bit late. Nonetheless, we start right now this session dedicated to mobile security, in which we have six contributions and 6 talks. And I just recall to the speaker that they have 12 to 14 minutes each for the presentation, so that we can have a little, say, a couple of minutes each for some question. Okay. And so, nothing. Let us start this session related to mobile security with the first speaker, Antonio Ruggia.
Hello, everybody. I'm Antonio Ruggia, a PhD student in the University of Genoa, and I propose you ARMAND, a novel anti-repackaging protection scheme, and ARMAND Droid, its implementation for Android application. In this talk, I'll describe the anti-repackaging threat model and briefly introduce the state-of-the-art anti-repackaging main components and their limitations. Then we will propose ARMAND and ARMAND Droid, its implementation for Android application. And finally, I highlight some future works. First of all, I introduce our threat model into the ecosystem. Currently, an individual or a company develops an application, create an APK file, and deliver it uploading to one or more app stores, such as Google Play Store. In this way, an Android user could search the app, download it, and execute into his device. Similarly to the final user, also an attacker can download the APK file from the app stores. The APK file contains all necessary information for the first run into a device. So an attacker can analyze the application and inject some malicious payload or modify the application behavior. So he can pack into a new APK file and upload it to one or more app stores. In this way, the final user is not able to discriminate benign from malicious application. In addition, an attacker can distribute the repackaging application, leverage side channels such as phishing emails. This process is known as repackaging. In order to protect application from this threat, the developers can inject some integrity controls into the application. These controls are known as anti-repackaging protection. Due to this control, during the repackaging process, an attacker should detect and remove all these integrity checks, and the attacker should test the application before distribute it into the app stores. In the state-of-the-art anti-repackaging techniques, there are 3 main components. The first one is detection node, which is the integrity checks that aims to detect any alteration of the target application. For example, in the detection node could be verified the signature of an APK file. The second main components of the anti-repackaging techniques are qualified condition, which are an equality condition, which are an equality check with one or one of the 2 operands is a constant value. Finally, the third main component is logic bomb. The logic bombs are an encrypted piece of code which hide some integrity controls. Malware, for example, leverage logic bombs for hide the malicious payload, and contrary to malware in anti-repackaging techniques, we leverage logic bombs to hide the detection node inside the application. In our work, we investigated the state-of-the-art anti-repackaging techniques, and we identify some limitations. In particular, a lot of them rely on a fixed pattern that can be easily identified from an attacker, and do not rely on a native code. The native code is more difficult to analyze or modify than the Java bytecode. In addition, the set of detection node is limited to at most 3 integrity checks, and the state-of-the-art anti-repackaging techniques rely on a single function to perform the integrity checks, causing a single point of failure problem. To overcome this limitation, ARMAND create multiple patterns into the APK file and inject several anti-tampering controls that rely on both Java and native code. Moreover, ARMANDs rely on semi-stochastic criteria to inject both anti-tampering controls and logic bombs in order to create a different version of an APK file at each protection process. Moreover, finally, we combine protection and obfuscation to guarantee an high-level protection, a high protection level. So we develop ARMANDroid, an ARMAND implementation for Android application. This tool creates 6 types of logic bombs based on Java bytecode, native code, and their combinations. In addition, ARMANDroid injects several anti-tampering controls into the application. We will show you the protection process through an example. In this video, we leverage the ARMANDroid Docker image to perform the protection of an APK file. This image is freely available into the Docker app. After the protection process, we sync the application and install it to the device. As we little demo show, the protected application works as expected, and there is no evidence of execution crashes or problems, despite several anti-tampering controls and logic bombs are injected into the application. Going in depth, in this slide, we propose an original method of the protected application. In this method, in the valid post method, there is an if condition, an if statement, in which one of the 2 operand match the qualified condition form. In particular, as you can see, the Java statement is translated into 2 nested if condition inside the SMARI code. And this condition matches the qualified condition forms that can be transformed into a logic bomb. So ARMAND detect this qualified condition and transform it in order to encrypt the content of the if statements. In addition, ARMAND translate the if operands in order to hide the encryption key of the if content. As we said before, ARMANDroid transform a qualified condition into logic bombs and inject several tampering controls into the application. In this slide, we report an example where some instructions of the original code are executed only if the environment checks succeed. Sorry. In particular, in this slide, we test the debuggable flag inserted into the manifest file. So we test our tool, ARMANDroid, in the wild over 30,000 applications. And in this slide, we report the distribution of the Java anti-tampering controls and the logic bomb injected into the testbed applications. Moreover, we report also the protection time and the size of the ret in megabytes of the protected app than the original ones. As we see from this slide, despite is injected, ARMAND injects several anti-tampering controls, the overheads in time and space is acceptable. Finally, in order to conclude, we propose ARMAND, a novel anti-packaging protection schema and its guidelines, and we develop ARMAND, its Android implementation. Its implementation for an Android application. As a future work, we can improve ARMAND to inject more logic bombs or inject several anti-tampering controls, or to fix some minor implementation bugs. And the ARMAND the guideline proposed by ARMAND, could be leveraged, or also to protect application in different ecosystems, such as application in iOS or IoT. And thank you. I'm going very quickly, and I hope that everything is clear, and you are welcome for any doubts or questions.
Okay, thank you, Antonio. We have room for a couple of questions if somebody wants to make some questions. I suppose, as far as I recall, that they need to be written to me, and then I can read them to Antonio, okay? In the meantime, waiting for other questions, I think that I have a question, indeed. The question is, what is the percentage, let's say, of in-depth analysis in the wild of application that fails when you apply ARMAND, and which are the main causes of these failures? Okay.
Okay, thank you for the question. I prepare another slide, and I'll show it. In this slide, we report the percentage of the protection failures in the left side of the slide, and around 7.8% of the application causes some exception during the protection phase. And in the right part of this slide, we propose a little graph where the main causes are reported. In particular, the light blue globe are related to generic errors, for example, implementation bugs or unknown errors from unknown causes. And the other globes are due to errors from third-party libraries. For example, the green and the blue gloves are related to Suite library, Suite framework, and the purple glove are related to XML library, which this library are leveraged from ARMAND to perform the protection of the application.
Okay, thanks a lot, Antonio. I did not receive any questions, so thank you for your presentation, and we can move on to the next presenter, which is Andrea. Thank you, Antonio. Please, Andrea, go on.
Yes. Just a minute. Okay. I think the presentation is available.
Yes.
Okay. Thank you. Hello, my name is Andrea Romdhana, and in this keynote, I'm presenting to you COSMO. Code coverage made easier for Android. I want to begin with an overview. I'm starting, I think, okay. I want to begin with an overview. I'm starting to explain some of the open problems concerning code coverage, and I'm continue exposing our solution, COSMO, and the achieved results. Let's investigate the motivations behind COSMO. First of all, Android apps keeps growing in complexity, introducing new features and services. And to properly test the applications, checking the code coverage is one of the critical methods. But to collect the code coverage of an application, we need to instrument it. And the automated tools available instrument the apps at the SMALI code level. However, inspecting the covered SMALI code is less significant for a developer than the evaluation of a covered source code lines. And no existing tools support Android instrumentation at the source code level. So what you need to do is to do it by hand. But is it comfortable or practical to instrument an app by hand? Well, let's see. First of all, you need to modify the Android manifest. Then you need to add the new dependencies. And then you need to create instrumentation classes. You need to modify build Gradle. And then you need to add a new Gradle task. And then, if you didn't do any mistake, maybe your app works. So we create COSMO, the first fully automated Android app instrumenter at the source code level. It can also operate as a black box tool, instrumenting the debug APKs. And it is based on Yacoco, and due to this, code coverage statistics are available for analysis and visualization in the widely used Yacoco format. Is it difficult to instrument apps with COSMO? Well, with COSMO, the instrumentation is smooth as silk. 2 clicks and you are ready to go. You just select the folder of the app. But how does COSMO work? Essentially, it automates all the steps that need to be done by hand. And to instrument the source code of an app, COSMO searches for the Android manifest, adds a broadcast receiver, then generates the broadcast class. And the broadcast is responsible for generating the coverage files. And then COSMO adds the Gradle task that converts the coverage file into a report. To instrument an APK, COSMO extracts the Dalvik bytecode, converting it into Java bytecode, and then it adds the Yacoco agent, re-instrumenting by instrumenting the app, and repacks the app. The runtime phase is very similar between the two methods. And we install the app, we interact with it, and when we want to generate a coverage file, we send an intent to it. That is simply a signal. And then we collect the coverage file, and we generate the coverage report. To evaluate the performance of COSMO, we selected 1,300 most starred apps coming from F-Droid, and we successfully compiled 61 of them, and 95% worked without crashing. COSMO from source has been evaluated on this set of apps, while COSMO from APK has been evaluated on a subset of the 60% due to a tool in the pipeline of COSMO from APK that is not compatible with multi-dex apps. To test the apps, we wrote a script to install, launch, and interact with the original apps and the instrumented counterparts. The script produces a sequence of actions that are replicated on the instrumented version. If the instrumented app can run for 10 seconds without crashing and generates the same execution trace as the original app, we define it as working. Now, if we consider COSMO from source, 89% of the apps worked. And the failure that we encountered regard only the build phase. So when we instrument and we compile the app. And these failures are mainly to old Java versions, corrupted resources downloaded during the download phase, or app misconfigurations. If we consider COSMO from APK, 62% of the apps worked. And speaking about failures, we have both build failures that are the failures given during the instrumentation, and runtime failures that are the crashes of the app. When you launch the app crashes. The build failures are related to a tool in the pipeline that does not work as expected. That is the DX tool. But also the build failures are related to some apps that were already instrumented. Speaking about runtime exceptions, they are mainly related to corrupted resources within the app. So something went wrong during the repack of the app. Adoption scenarios. COSMO can assist developers during their apps testing phase, because by examining code coverage reports, the developers can write more effective tests. But also they can compare alternative automated test generation tools on their app instance. But moreover, researchers can use COSMO when developing novel test case generation approaches. For example, you need to test a new automated testing tool. For example, a new Sapiens or a new Monkey, and so on. To conclude, I've presented COSMO, the first fully automated Android app instrumenter that works both on source code or on APKs. It is compatible both with Java or Kotlin. And COSMO is available as an open source project on GitHub, by following the QR code in figure. Thank you for your attention.
Okay, thanks a lot, Andrea. Thanks for the speech. I don't know if there are questions. In this case, I'm not able to receive any questions so far. So this is just a very simple question, coming back also in this case to the problem of failures. Okay, the question is how much of those failures depend on the developer themselves? I mean, are they related to issues that the developer can try to solve, or are they related, for instance, with external libraries maybe imported in the application that, okay, let's say if you want to use that library, you cannot use COSMO because COSMO fails? Okay,
well, speaking about COSMO from source, the majority of build failures are related to app misconfiguration. And these app misconfigurations can be solved by the developer, and it is quite easily to resolve these problems. Speaking about corrupted resources or all the Java versions, it's the same. You need just to update your resources or your Java version. Speaking about COSMO from APK, most of the problems are related to the tools used in the pipeline. So it is difficult for a developer to modify the source code in order to have a compiled and working APK coming from COSMO from APK.
Okay, thanks a lot, Andrea. Thank you very much. I don't see other questions, so I think we can move to the next presentation. Since we are trying to reach an important target, so this means being in time, and you are in time right now. Okay, so the next speaker should be Eleonora. Are you there, Eleonora?
Yeah, Eleonora is is another co-author, but I'm the one.
Welcome, Marco. Sorry.
Yes, don't worry.
Okay, you're welcome. Please go ahead.
Okay, I'm using a two-computer setup because I had some small technical issues, but I think there will be no problems. I'm just sharing the video of myself from a PC and the voice and the presentation in another. So it should be good. And if there's anything problematic, just tell me.
No, everything is fine. Thank you.
Perfect. So, hi everyone, I'm Marco Casagrande, and with Mauro Conti and Eleonora Losiouk, we work under the SPRITZ Security and Privacy Research Group at the University of Padova. We focus on cybersecurity and will be presenting ACTGuard, preventing relay attacks against contact tracing apps. So, we're talking about a very pressing issue. So, okay. Contact tracing is a medical procedure which consists in identifying and monitoring individuals exposed to a virus. This is done in order to contain virus hotspots. And with automated contact tracing apps, try to make this process as automatic as possible, of course, because of the pervasiveness of smartphones in our modern world. Many governments jumped on the train of contact tracing apps and endorsed and actively developed their own contact tracing app. And in our case, we have Immuni, the official app of the Italian government, which we used as our case study. How do contact tracing apps work? They utilize a proximity tracing protocol, which is the inner logic of those apps. There are two main approaches for proximity tracing, the centralized approach and the decentralized approach, even though both utilize a central server, so the name is kind of misleading. We will be focusing on the decentralized approach because Immuni and other GAIN-based apps, so Google and Apple Exposure Notification System, which is a framework supported by Immuni, used a decentralized approach. So that's why we are talking only about decentralized in this talk. Whenever a user installs the app, it generates a secret seed from which the app can derive identifiers. Then, when users walk and meet each other, the app constantly broadcasts packets, usually Bluetooth Low Energy packets, and exchange those identifiers. Whenever a user gets diagnosed as positive to COVID, he can upload the secret seeds he generated to the health authority server. And the health authority server is able to derive the identifiers. And then the apps from other users regularly check with the server if there are any new identifier uploaded, because all those uploaded identifiers are from only positive people. So if the locally stored identifiers match with the identifiers on the server, that means that the user was nearby a positive individual in the predefined slot of time. So that's how contact tracing works, and in this case, the user would receive a risky notification message. We surveyed quite a lot of contact tracing apps from the governments and other. This is a table just to summarize some of them. In particular, we have, for example, the first one, Trace Together, which was the first contact tracing app in Singapore, which utilizes the proximity tracing protocol OpenTrace, the Bluetooth Low Energy packets. This is how the packets are exchanged, and the data shared with the central server, in this case, is the phone number. So quite it is a privacy concern, of course. And then we have the column with the weakness to reattacks, which was our main objective, to prevent reattacks. And we have found that most of the apps are vulnerable to reattacks, apart from one protocol which was developed by, I think by MIT, but well, this packed proximity tracing, which is protected, but was not used in any contact tracing app apart from maybe an autonomous one in USA. So not very largely used. And in particular, we have Immuni in the last row, which used as the GAIN. So I already told that is the Google and Apple exposure notification system. And it is vulnerable to the attacks, of course, as most other European apps, because they all use GAIN. We designed a threat model in which we have 2 places, which can be far away. We have 3 honest users, A, B, and C, and 2 malicious attackers, adversary 1 and 2, and the centralized server of the health authority. B and C utilize Immuni, utilize apps like Immuni, for example, and exchange the identifiers. In this case, we call it rolling proximity identifiers, RPI. This is just an identifier. So B stores the identifier from C, and C stores the identifier received from B. Also, we have the adversary 2, which is a stalker and follows B. It receives the broadcasted RPI from B and replays it to the adversary 1 in another place. The adversary 1 just replays the very same packet, impersonating B, and A, which is nearby adversary 1, receives the RPI from B. In this way, whenever B gets diagnosed as positive, he will upload the secret seeds to the health authority server. In this case, we call them temporary exposure key. And the other users will download them. C downloads the tech, derives the RPI, and see that it matches. And this is correct because B and C were in the same place at the same time. So that's good. And C receives a risk exposure notification. Then we have A that does the same and downloads the temporary exposure key, the secret seed, and finds a match because she memorized the same value as C. In this case, it is wrong because A was nearby adversary 1, but not B. So that's how a reattack can be performed, and it will be always effective on this kind of apps, or at least on this kind of framework, the Google and Apple framework. So we developed ACTGuard, which works together with GAIN-based apps. It calculates a hash with 4 elements, the RPI of itself. It utilizes the RPI of itself, the RPI from the other user, which was broadcasted and received by ACTGuard, the current user location, and the current time. ACTGuard uploads those hashes whenever a user is found positive to the server and maintains the same privacy and anonymity level because it just shares hashes. So even though we use the current location information from GPS coordinates and the current time, the hashes are not easily reversible. So the information is protected. But thanks to this embedded information, we are able to detect relay attacks. So here's a couple of scenarios in which users now are using ACTGuard. This scenario follows the threat model, so the relay attack is performed as shown before. But this time, B has ACTGuard, so it calculates the hash of his encounter with C. So we have the hash of with the RPI of B, of C, the place epsilon, and the contact, the current time of the contact. And the same is valid for C. So they store the same value. A, which is victim of the early attack, this time memorized the hash with place X as part of the hash. So whenever B uploads all of his hashes, he will upload the hash of the encounter with C, but not upload any hash which matches hashes stored by A, because B was never nearby A, and this time this element, the place X, blocks the adversary one from fully impersonating B and from making A receive a risk exposure warning. In fact, the official app still sends the risky exposure notification messages, but ACTGuard does not, because there is no hashes matching. So due to this incongruence, we can detect the attack and alert A that yes, you received a risky notification, but ACTGuard found that it was a fake notification because no hashes were matching in ACTGuard. Of course, in the scenario in which B does not use ACTGuard, we do not have any additional information, so we can't really help A in deciding if the risky notification is right or wrong. So we suffer from the same limitation of the contact tracing apps, so the adoption rate. And now I want to finish with a small demo with the proof of concept of this array attack, showing everything I've talked about in the scenario. So we have B, the honest Immuni user, which is currently broadcasting a RPI, so RPI of B. The adversary Chu, the stalker, is nearby. It utilizes our proof of concept malicious layup, which can detect any GAIN Bluetooth low energy packet. It can see the content, so for example, the RPI, most importantly. It uploads it to the internet so that the other adversary, adversary one from another place, can download it and impersonate B using the very same RPI. So adversary one is impersonating B this time. When another user is nearby, in our example, it is A, she will store the RPI from B just as the normal behavior of Immuni. Then, since A utilizes ImmuniGuard 2, our solution, it will also store the hash of the encounter. So the hash using the RPI from herself, RPI of A, the RPI received, so RPI of B, the spoofed one, her location, and the current time. Later on, B gets diagnosed as positive and uploads to the health authority server through Immuni its secret seed from which one can derive the RPI, and they receive the risky exposure warning. And then B uploads the hashes too to our ImmuniGuard server. Then A tries to find any matching hashes from her local database and the ImmuniGuard server. Of course, she will not find any match because it was she was being targeted by a relay attack. And since Immuni sent the notification, but ImmuniGuard did not, this incongruence shows that the relay attack was performed. Okay. So, in conclusion, in our work, we reviewed proximity tracing protocols and popular ACT apps, in particular the ones developed by governments, and most importantly, the Immuni app, the Italian one. We developed this proof of concept for relay attacks against Immuni and other GAIN-based apps, and we designed and implemented ACTGuard, our lightweight defense mechanism against relay attacks that is able to detect them. Of course, our solution has some weaknesses. The most important one is that it is difficult to extract the RPI from itself. So we plan to extend this work by implementing virtualization techniques and running the Immuni in a virtualized container in order to extract the RPI by having the full control of the app behavior. So that's our proposed solution for our most important issues. So, of course, contact tracing apps had the spotlight, but quickly it went away. But we hope that by improving their security, we will improve their effectiveness in the hopefully not hopefully in the future epidemics, but hopefully not near future at least. So that's it, and thanks you for your attention. And if you have any answers,
thank you. Thank you, Marco. We have indeed some questions. We have a question from Riccardo Lazzaretti that says something like this. I suppose that GAN relay introduces a significant delay. Can we use the difference between the transmission time in the message and the receival time to immediately detect the attack?
Okay, so how does the time slot of GAN packets work? GAN packets have two elements: the RPI and a slot validity slot. So you have the secret seed. It generates for every 15 minutes, I think, or depends on the implementation, the identifiers, and they are only valid if received in this time slot. Even though you have an identifier for every 15 minutes, they are still valid for 2 hours, at least at the last time I checked. So yes, you could use the time, but since the Windows is very relaxed, 2 hours is quite a lot for this kind of attack. It is not quite good. Yeah, you have to rely both on location and time, in my opinion.
Okay, thank you. I have a couple of considerations, very, very quick. The first one seems that the problem of this attack is basically the protocol level. So according to my perception, and maybe I'm wrong, the problem is not in the application themselves, because they need to rely on the, let's say, protocol for exchanging these Bluetooth beacons and so on. Okay, and so in this case, if I'm not so wrong, let's say, I'm just guessing why that application safe, I don't remember the name exactly, was secure in this case.
Okay,
they applied
yes.
something that you applied for securing, maybe something based on hashes and so on. And this is the first question.
Yes, the main issue for relay attacks is that in order to fight them, you need some additional information, and in particular, you need some form of let's say, lightweight authentication. And if you want to address the privacy concerns of the citizens, you have to share the least information possible. So safe paths, in this case, yes, it was robust against relay attacks, but it also shared more information. They still used some kind of hashes and tables and so on, so more complex than our solution. And you are proposing this one because it's simple to grasp, and you know that we are not doing anything malicious behind. But yes, they do use you were right. You were right.
Okay. And very last consideration, I think I've seen just a step of your protocol, enhanced protocol, to be robust against this relay attack. I'm just asking you if you just try to prove formally that this protocol is secure against man-in-the-middle attack, because this is the man-in-the-middle attack. Maybe uses SATMC or something like this, because maybe just hashing cannot be robust enough. For instance, you encode the time. My question is, if you reply the same hashed message the next day at the same time in the same place, can you just in some way trick some other citizen that think is near just a positive one, and this is not the case? If I replay the same message in the same place the day after.
Okay, so even though there is quite a few pages, quite a few pages of documentation, it is very difficult to know and understand what's happening on Google and Apple framework and on Immuni servers and so on. So and also there is the legal issues that we cannot kind of attack the health authority system because they are busy with other stuff. So a formal trial is very difficult. Our proof of concept currently is kind of weak. I just use MD5 in order to do the hashing. So of course, in our extension, the second point is to try effectively performing this attack, seeing in some places with people willing to participate in the experiment if the signal is strong enough, if an attacker can just sit in the same room, in a different room from far away. So yeah, it is not quite as robust as we'd like. You are right,
Okay.
but we are trying to improve and test the limits of this protocol.
Okay. Thank you, Marco. So I have a question. I forgot a question from another participant. Luca is asking, I was wondering how you can determine if a user is near to another one as the location is stored as an hash value. Does this system require also to store the information in the original form? For instance, means not hashed because you need to have a plain track of the position, I think.
Okay.
It's very quick because the time is running out.
Yeah, sure. Yeah, the GPS location is just a number, so we can truncate the last numbers in order to adjust how much specificity we want. We can do the last one to be precise in meters or entire cities. So we use this value, and since the two people should be in the same circle, let's imagine the GPS coordinates as a circle, they will have the same values. So if I'm nearby you, we both have 1000, 1000 as our x and y epsilon y coordinates, and with the same input, we receive the same hash output. So it could be mismatching. Maybe if you are you have some GPS signal interference, but I think that mostly it will be good enough.
Okay, okay. So I think that the resilience, the robustness depends on how many numbers you trunk, I think, in the GPS position. Okay. Yes. Thank you, Marco. Thank you very much. So we can move on the next presenter, which is Giacomo. Maybe, am I right this time?
Yes.
Okay, Giacomo, please. You're welcome.
Yeah. Okay. Can you see the slides? Okay. Can you see my slides, right? And can you hear me also? Yes, I guess so.
Yes, I can see the slide and hear you.
Okay.
Since nobody is.
Yes.
Thank you. Thank you. Okay, I'm gonna start. Good afternoon, everybody. I'm Giacomo Iaderola. I'm a PhD student from the Institute of Informatics and Telematics of the CNR in Pisa. And today I'm here to present, also on behalf of the other authors listed in these slides, one of our most recent works that is talking about interpretability and the role of the interpretability in the malware context, especially in Android environment in this case. And I had prepared a couple of slides to motivate the explicable AI, but I've seen a couple of really good talks in ITASEC here on the importance of the interpretability and so on. So I'm just gonna be super quick in this. And just to show you that I took this information from AV-Test and Kaspersky, that in the last year, there was a huge increase of banking malware in mobile environment, and also on the type of malware that are like adware or the so-called potentially unwanted application. So all these applications that are abusing actually the trust of the user. And this is because probably many users were forced to start using, I don't know, mobile banking, for instance, because they were during the pandemic, they weren't able to go to the bank, so they start using the online banking application, and that's, of course, is really attracting for attackers that are interested in stealing information if there are more users that are using a specific app. Fortunately, we have a lot of techniques, static, dynamic analysis for malware analysis, and in the latest years also artificial intelligence has helped us a lot to classify malware and detect malwares, and this is really good. But one of the biggest controversies about this is the adoption of these models as a black box, because we know that many security analysts sometimes, they trust the prediction without really understanding the reason of a certain choice. And this is really dangerous, because then we have to we want the user to adopt our technologies, but we are the first one that are not 100% sure of a specific prediction. And we have seen in this year that during the pandemic, there were so many good technologies that were being approved by the scientific community that are actually kind of useless because people don't trust these technologies. And so that's the importance of the understanding the technology, and that's why the research in computer science as well is moving towards interpretable models. And when I say interpretability, I mean the degree to which a human can understand the cause of a decision, and that's why our work here is based on a specific kind of interpretability, which is the outcome explanation. We are not interested in understanding the entire model, but just to give a reason of a specific output given a specific input. And that's is based our proposal, which is a malware family detector based on a standard convolutional neural network, on which we have added a couple of steps in the model assessment, in the selection of the best model, including a GradCam to assist the security analyst in choosing the best model, also evaluating these models with regard to the interpretability and reliability, together with the standard accuracy measures of the deep learning models and so on. And that's like the methodology. The idea of the methodology that can be split in two parts, the standard model training step, and also we added a couple of explainability, so-called explainability steps. The first part is pretty straightforward. I just want to focus on the data set. In our case, we have represented malware as images. So we have converted the binary sequences to images. This is a standard techniques that have been applied many times in the literature. Then in the model assessment, we have started adopting the convolutional neural network. We have tried different hyperparameters, also different architectures and so on. And we have performed many series of training, evaluation, validation, test, and so on. And then we want to add also an explainability step in order to choose the best model, also based on the reason why the model performed that specific predictions. And for doing so, we actually adopted the GradCam, the gradient weighted class activation mapping, which produce a localization map that highlight the important regions for a prediction. This is widely used in standard image classification problem. Here, for instance, there like a picture took from the paper of the GradCam. When there is like the original image, then there is an image that has been predicted there is a cat in the image, and the localization map, the heat map, actually highlight the cat. And so we know that the model was looking specifically at the cat for performing that prediction. In our case, we have this situation. Here on the left, there is the malware converted to an image. And then we give this malware as input to the model. And then we perform the classification. And then we can also, in this case, generate a heat map that gives us information on the prediction that the model has done. In our case, for instance, in this example, the heat map is saying that this area, which corresponds to this area in the malware, was really important for performing the prediction. And of course, there's no a specific shape, there's no specific animal in the malware image that is recognizable. So we need to find a way to use this information that actually the model is giving to us. And first of all, we try with the so-called cumulative heat maps. We selected a subset of sample from the test set of the database, of the dataset, and we actually overlay all the heat maps generated pixel by pixel and generated a unique heat map that is actually merging and giving the idea of the inference for an entire class, for an entire malware family in this case. Of course, it can happen something like this, since this image has been created by just overlaying different images, it looks like random noise. But in some cases, it can happen something like that, like the picture on the right, when this image has been created by merging many images, but it doesn't look like random noise, but it seems that there is a specific area for that entire specific malware family, which is really important. And this information could be used by the security analyst to check on the original malware, that area corresponds to something, and so on. Of course, this requires a prior knowledge on the malware itself. That's why we try also to produce some information, some value to actually compare the interpretability, let's say, and the information that the model is giving to us without having prior knowledge on the dataset itself. And the simple idea is to produce image feature vectors from the heat maps and then compare the heat maps one to each other and evaluating the distances using Euclidean distances. By doing so, we can compare heat maps coming from the same malware family and also heat maps coming from different malware family. And then we can choose the best model as the one that is producing similar explanation for sample from the same family, and also that it's produced different explanation for samples that are actually coming from different families. To test this idea, we collected a dataset of samples coming from the Android malware dataset. And we add also a class for trusted. And this is just an extract of some results that are reported in the paper. In the first table, there is the standard measurement evaluation for the deep learning models. And here they are reported 4 lines. Each line is a different model that has a slightly different, they are all convolutional neural networks with slightly different hyperparameters. And as we can see, also the performances are slightly different, but the model number 2, it seems to show the best results, the best performance. But in the end, we decided to go with the model number 4 because we evaluate also the second table. And as I say, this is just a part of the second table because it contains only 3 families, but the complete table is on the paper. And this table contains the information on the distances between the heat maps. And since the heat maps represent the explanation, represent the inference phase of the model, we can compare the model and different models on that. And for instance, we can see that the distances, the average distances for heat maps on the families is smaller on the model 4 compared to model 2. And on the other side, we also tried with the so-called mixed folders, who are a set of heat maps coming from different malware family. And in this case, we can see that model 4 has a bigger distances between these heat maps, is able to create different explanation, different explanation than model 2. And so in conclusion, to recap, it was just a small contribution to support the idea to start including also interpretability as a model evaluation metrics, and we contributed by just showing the feasibility of some explanation techniques that are adopted in image classification, such as the GradCam, also in a malware detection context like that. And of course, we would like to improve this interpretability measure. And the first idea is going to be reversing the process and using the information that the GradCam is giving to us to actually analyze the code, analyze that specific area on the original malware. And that's all. Thanks for the attention. And if there's any question, they are welcome. And just as a last point, I'd like to say that all the code is available online on GitHub and can be applied on convolutional neural network, but also other deep learning models to generate all kind of these calculation and interpretability measures.
Okay, thank you, Giacomo. We have time for some questions. I have a request from an attendee to come back to slide number 10. I don't have a question right now, but just a request to move, just to have some details. And I have just a question, okay?
Yeah.
What I didn't get, maybe because I lost something, is you build this heat map from the APK, from the bytecode, from the Smalley code.
It's actually from the bytecode, directly from the bytecode in this specific paper. But we are working on an extension, and we have worked also on Smalley code. But in this specific one is bytecode. It's just the DEX file extracted from the APK. Okay, so the main criticism I can do this just for procedure for the next step of your research is that if you have a malware that embeds something in a native part, you're not able to detect it. Yeah. I do agree. So the simplest way to let's say to avoid your methodology just put up very stupid payload in a native library. Yeah, that's true. Yeah. But actually, the main point of this work is to show that we can adopt some technique to improve the choice of the best model, and also taking into account the interpretability. Of course, I'm perfectly aware that this is not the best classification techniques in general. And also because we have used, standard, it's not even a so big data set, to be honest. And there are not even so many different families. It's just an example to see, okay, we have 2-3 models that have similar accuracies. Which one is the best one? And our idea is we need to take into account also interpretability. We also to see why this prediction has been done. Okay, and the last question is coming back to the set of the samples, okay? Yeah, the set of samples. The sample, the data set of malware. Okay. Yeah, sure. Yeah, okay. Sorry. Which is the here, let's say, the here's of this malware? How old are they? This is the question. Android malware dataset is 2018. It's actually collecting samples from 2016 to 2018, I guess. And actually, there is another problem with this dataset now that I'm mentioning, because I've checked yesterday, that is actually offline. I don't know why, but the website is offline.
Okay. So just a very last suggestion is to maybe compare your approach with other existing approach which do not leverage machine learning, for instance, on Android, because Android malware on Androids are basically not binary like in the classical case of Windows and so on. So there are other approaches to detect malware coming from decompiled APK and so on, and maybe you should take into consideration the differences between your machine learning based approach and the other. Okay, that's all. Okay, we can move. Thank you, Giacomo, for your presentation. So we can move to the next speaker. Okay. I don't know who is the speaker of security IoT pairing.
It's me, Giovanni Salzillo. Can you hear me?
Okay, Giovanni. Well, yeah, okay. We see you, so you can try to share your screen.
Let's try. Okay.
Yeah, we see your screen, but not the presentation right now.
Someone. Okay, can you see my presentation now?
Yeah, please go ahead.
Okay, thank you. Good evening to everyone. I am Giovanni Salzillo, and I am a PhD student from Università di Studi Luigi Vanvitelli. And today I'm going to present you our work about IoT security and mobile application, in particular on security aspects of authentication and pairing protocols. As you know, the number of wireless smart devices, and in particular the ones equipped with Wi-Fi modules, is continually increasing. And according to Amazon, in 2008, more and more objects are being connected to the internet, and more than 50 billions of devices are expected to be connected in next years. Also, new protocols are being developed to simplify the configuration and the pairing procedures of these devices. And a significant effort has been put in the last years by vendors to improve the user experience, often underestimating other aspects such as security. And as there is no standard reference architecture on IoT pairing, the basic question we try to answer, at least with this preliminary work, is whether these protocols, in particular a specific pairing schema, are secure, and whether people are aware of security risks which are exposed to. So to summarize our contribution, we propose a general threat model for the IoT pairing process. We performed a preliminary validation of this threat model through a threat-based security testing approach on a real device taken from the market. And this led in particular to the identification of a vulnerability and the registration of a public CVE ID. Finally, we propose a set of recommendations and mitigation against the problem we identified. According to FOMICAV, a general pairing schema consists of 3 steps: the discovery step, the secret exchange step, and the verification step. I would like to make you notice that these 3 steps do not have to be carried out on the same physical channel. Also, multiple channels can be involved. The discovery phase is devoted to the device identification, the mutual device identification. The secret exchange is devoted to the creation of a secure communication channel, and the verification is where the involved entities verify the shared secrets and verify that the process has not been tampered. This last step could also not be always implemented. Among the existing pairing schema, we're interested in those that pairs an IoT device to a Wi-Fi network. Note that the image on the left is just a basic schema. However, in a typical IoT scenario, you can find multiple instances of this schema. For example, think about a scenario where you have that involves a smartphone, and this smartphone wants to configure the IoT device through, for example, a mobile application. So you have an instance of this schema between the smartphone and the device, and a second instance between the device and the target network. Among the technologies and the protocols that could be involved in this configuration processes, we already analyzed in the past the security of the smart config product family and ZigBee protocols in an Alexa home automation system. And as for this work, we will focus on a particular schema that involves just these two technologies, namely the access point mode, also known as the soft API, and an out-of-band channel, in this particular case, a QR code-based human-computer interaction. This is the generic schema that we are considering that involves a generic human communication, human-computer interaction, and an out-of-band channel for the discovery phase. So you can look at the steps 1. Okay, these steps involves also the acquisition of a shared secret through the out-of-band channel that is later used to authenticate the communication. The smartphone retrieves also some device information from a remote service and shares the network credential to the IoT device, which in turn connects to a Wi-Fi network through a Wi-Fi network association. Later, the device is able to contact the remote service and register itself to the remote services. Okay, our work focuses on the security analysis of this particular schema, and this is the methodology we used for the security assessment. This is a 4-step methodology in which the first step, the system modeling, is a step that is devoted to the description of the system under test through the MACM, which is a formalism, a graph-based formalism we developed to describe system and components. This is a methodology, this is a threat-based methodology, and the second step is devoted to the threat identification and quantification, whereas the last 2 steps, the planning and the execution and the implementation, is devoted to the actual attack planning and attack execution. Well, as I said, this is a threat model-based methodology, and this is an except. This is a piece of our threat model that we enriched with the threats concerning the IoT pairing. And this model is enriched with extra attributes that we removed because of space reasons. But we also has attributes such as the confidentiality, integrity, or availability attributes, or the stride classification. The involved assets are the Wi-Fi network, the IoT device, the user equipment, and the remote service, which are all present in our schema. Among the identified threats, let me focus on those that are highlighted because these are the ones that we implemented in our case study. So T4 is an eavesdropping threat by which a malicious user could retrieve valuable data from a network sniff. T6 and T15 are 2 data leakage threats by which a malicious attacker could retrieve data from a vulnerable device in T6 and from a remote service in T15. Now let's see a concrete implementation of these threats in our case study. For our case study analysis, we selected the Sonoff Micro, which is a device marketed by Etihad. It is one of the most popular USB smart power switch. It can be connected to your smart, for example, to your smart charger. It can be programmed to cut off the power switch at a certain time schedule. Although this device is sold by Etihad, this device is controlled through the EvoLink mobile application. EvoLink is actually a big hub platform that supports more than 80 brands, including Google and Amazon home automation systems. In this figure is represented the QR code pairing mechanism for the Sonoff Micro from the user perspective. Basically, the user power on the device into pairing mode, and through the mobile application, the AirWlink application, he scans the QR code, inserts his Wi-Fi credential inside the application, and let the magic happen. If we look at the schema, the deeper details, while looking at the comparison, the steps from 1 to 5 on the left are directly mapped on the first step of our generic pairing model. The 6th step, instead, on the left, is mapped on all other steps in the pairing model. And this makes sense since the low-level device pairing configuration do not require any human intervention. So let's look at the protocol implementation details. We started from the QR code, which we found encoding an URL. This URL did not result to any internet resource, but instead, if you look closer, you'll see an SSID, which encodes the actual device ID. In the next step, during the initial step of the pairing schema, so I'm talking about the human-computer interaction, we found that the smartphone queries a remote cloud service. You see there is a different URL with device ID parameter. As a result, the remote service gives back a secret key, gives back a JSON encoding multiple information, and in particular, you'll see a secret key. This key is used later on in the next steps because for what concerns the remaining steps, in particular those that are automated by the application, the smartphone automatically connects to the IoT Wi-Fi access point, and it can do this thanks to device ID that is contained into the QR code. And next, it encrypts the Wi-Fi credential that are inserted by the user through the advanced encryption standards, and using the secret key that is previously retrieved from the remote service as a key for the advanced encryption standard. And this encrypted data is then posted with an HTTP post request to the device to the device web server. Next, the device connects itself to the client Wi-Fi network. Well, the fact that device esteems its device ID as the Wi-Fi SSID enables a nearby attacker to implement all the three threats that we presented earlier. And in particular, if you consider this scenario, a nearby attacker would be able to identify the device ID by solely looking at the Wi-Fi in his nearby. He could be able to eavesdrop on the configuration message, this one here, and although it is encrypted, he will be able to decrypt this message by querying by itself the remote API endpoint, the cloud service, with the device ID that he took from the SSID. As a result, he will be able to decrypt this data payload and extract the target Wi-Fi SSID and password. Then he will be able to compromise the entire Wi-Fi network of the final customer. But the main problem here is that the QR code does not encode any security information that is related to the device, but instead a public service endpoint is called to retrieve the device secret key, and is actually open. This vulnerability, note that, is exploitable only during the device association and by a nearby attacker. However, in case of a successful exploitation, an attacker will be able not only to compromise the device, but the whole Wi-Fi network of the final customer. And users can do much to protect their Wi-Fi network credential while using this pairing mechanism, because there is no fallback mechanism, no fallback pairing mechanism. Also, the same vulnerability is expected to be present also in other EULink code-based devices. And a solution could be to encode the secret key directly inside the QR label. But there is still the problem of what would happen if the sticker is lost. We also touched a disclosure timeline with our report to EULink. And finally, EULink acknowledged back our report, and they were addressing the problem. In particular, they should have implemented, according to them, a short-term monitoring solution before a complete API design. To conclude, as a general rule of thumb, please do not statically wire your encryption key inside end user devices, application, or web service, because security by obscurity can protect. Also, do not leave open security related endpoint, and use known security key exchange protocols. If you can, please, before shipping to the market, perform a deep threat analysis. As a future work, we are planning to support and analyze other protocols and generalize our security analysis approach to support also other protocols. And that's all.
Thank you, Giovanni. Very interesting vulnerability. I didn't receive any question. I have a very, very quick question on the methodology that allowed you to discover this vulnerability. Is this analysis methodology carried out automatically, or did you find, let's say, the vulnerability manually inspecting the packets?
No,
so
actually, it's manual, because the methodology is threat-based. So we start from a high-level threat model, and we get an instance of this threat model for the particular case study. So we try to implement those attack plans, okay, for each case study. At the same time, we enrich our catalog, or at least our testing knowledge base. So we have actually a repository of these testing cases, and our plan is in future to automate these steps. So automate the instantiation of these test cases for the scenario that we are going to analyze.
okay, thank you, Giovanni.
Thank you.
Thanks for your presentation. Now it's time. We're a bit late, but not too much, for the last presentation.
Okay.
Okay.
Yes, I'm going to share my screen. Just a moment.
Okay, Rocco. Yeah,
Okay.
everything goes fine. You can go ahead.
Okay. Can you see? Okay. Hello everyone, I'm Rocco Zaccagnino from University of Salerno. This work has been done in collaboration with De Brisco and Alfredo De Santis. This is the outline of the talk. I will start with an introduction, then I will discuss the threat model and our settings, and I will provide some details about the two main contributions of these works, that is a deep learning-based speech units recognizer and the generalization to entire words. Finally, I will conclude with some concluding remarks. Okay, let's start with the introduction. In this work, we face the problem of inferring speech private information exploiting the smartphone accelerometer. Accelerometer is one of the most studied motion sensors in literature. It is normally considered not dangerous, and because of this, its access is generally unrestricted. So we focus on the speech recognition by measuring the accelerometer signals. We remark that most of previous work mainly focus on recognition of single letters, digits, or odd words, while in this work, starting from some relevant related work, we make a preliminary step towards the recognition of entire words. As we will see, we assume that every word is obtained as a combination of speech units that are the basic components of a language. So So, as proposed in previous work, we decided to use the spectrogram representation of acceleration signals for recognizing the speech units. And so the main contribution of this work are, first, an over deep learning-based system that using a simple custom convolutional neural network learns to recognize the speech units, and also a preliminary, simple general method for recognizing entire words in speech conversations. Several experiments have been conducted in Android, on Android platform using Spy app, which is an Android app we have developed to collect the accelerometer readings. Okay, now I'm going to show you the trait model and the setting. Most previous work, the device emitting the sound, in general another smartphone, an external speaker, is different from the one that captures the accelerometer readings. Another interesting case, also considering these works, is the one in which the two devices are the same. That is, the same smartphone is used both to reproduce speech signals and to record the accelerometer readings. These settings, referred as table setting, imagining that the device is placed by itself on a table, is used to have measurements that depend only on the sounds being reproduced. Also notice that this can be considered a realistic scenario in, for example, office or of environments where the conversations are often based on the exchange of voice messages. So this figure shows the trait model. We assume that the victim's smartphone contains a spy app that measures the accelerometer signals during the reproduction of a speech, whatever the source of the speech is. And so at this point, the main goal of this work is how to infer the words intended as combination of speech units from the captured measurements. To reach this goal, we propose the strategy consisting in two main steps. We first define the deep learning-based speech units recognizer, and then, as we will see, we generalize such a system to recognize entire words. Okay, well, some preliminary definitions. Speech units are the basic components of a language which combine to produce words. For example, in Italian language, the speech units are the digits, letter, and syllables. And so we have considered the following classification problem. Given the accelerometer measurements of a speech unit reproduced by the smartphone, recognize the speech unit. How to solve this problem? The idea is to represent accelerometer signals as image and exploit the powerful deep learning models studying the computer vision. To this, we have followed a standard methodology consisting in several steps. During the first step, the data collection, the accelerometer signal measurements were collected using a Samsung S8. We have used the table settings described above. We have considered 31 speech units in Italian language shown in this table. For each speech unit, we have collected 1,200 samples for a total number of 37,200 measurements. Following in the next step, the preprocessing, the goal was to find a suitable representation for the accelerometer measurements. That is a representation that can be effectively learned by deep learning models. As proposed also in other related work, we decided to use the spectrogram image because it reflects the multi-scale information in the frequency domain, and it is very useful for widely adopted modern in computer vision. So for the preprocessing, we followed a standard transformation pattern, which makes uses of a linear interpolation and high-pass filtering first, and then a signal to spectrogram and a spectrogram to image to obtain an image which represents the accelerometer measurement in a time interval. Following the last step, during the training, validation, and testing, the first problem to solve was which model, which convolutional neural network to use. Just a reminder, convolutional neural networks are multi-layer neural networks designed to recognize visual patterns directly from pixel images. For our experiments, we are considered both well-known standard convolutional neural networks, often so deep that it is difficult to visualize the entire model, and by running several tests, several experiments with ad hoc combination layers and parameters, a custom convolutional neural network that, as we will see, outperforms the standard ones. In summary, the custom network consists of 12 layers, 3 pairs of convolutional max pooling layers with the ReLU function, a dropout layer which generates vectors of 1024 elements, which is given to an input to a flattened layer, which is fully connected to two dense layers interconnected to an output layer of size 31, which is the number of speech units considered. Okay, we have followed a standard approach in which we have used a training set consisting of 18% of the images in the data set and use it for training and validating the chosen networks, and also a testing set containing the remaining 20% of the image used for the testing phase. In these tables, we show the results obtained. Best results are highlighted in bold phase. In summary, the custom network outperforms the other models with respect to all the metrics considered, with an evident improvement during the testing phase. Also, we observed the over-parameterization issues affecting the standard convolutional neural networks, which prove that for the specific problem considered, a model with a simpler structure can achieve a higher generalization ability. In the second step, we have generalized the recognized capabilities of such a systems to words. We recall that that most previous work directly consider hot keywords, as an example, the word password, username, social, and so on, with a critical issue that is adding new words requires rebuilding the model, and reaching a now set can be quite difficult. So we proposed a very simple solution. The idea is borrowing, given a sequence of speech words and the corresponding accelerometer measurements, we first adopt some design segmentation technique to identify the sequences of syllables corresponding to actual words. And then we use an extended recognizer, speech unit recognizer, able to recognize the syllables. So we each syllable obtained in the segmentation step is given as input to this recognizer, and finally we are able to reconstruct the original words. So in this simple solution, for our experiments, we have considered 20 dummy syllables shown in Italian language, shown in this table, and the words obtained can be considered as dummy words. We have repeated the training, the validation, testing phase by considering the same dataset, but using the same dataset by considering the 20 classes corresponding to the 20 syllables instead of digits and letters. In this table, we show the results obtained. Best results are highlighted in bold phase, and as we can see, results are similar to those obtained for the digits and the letters. That is, the custom convolutional neural network always outperforms the other networks. Finally, we also tested the recognizer using a set of 100 sentences of varying length from 5 to 60 seconds. Each sentence is a sequence of words built using from 2 to 4 syllables per word. As a simple segmentation technique, we decide to segment each sentence with several values for the segment, for the length of the segments, and for each sentence and for each length, chosen length, the segments obtained are given an input to the extended recognizer. In this figure, we show the results obtained in terms of percentage of recognized words as a function of the length of the sentences on the x-axis, from 5 to 60 seconds, and for each of such length as a function of the length of the segments from 0.50 seconds to 0.70 seconds. In summary, the recognizer performs better with sentences from 15 to 45 seconds. The performance tends to degrade for long sentences. In general, the segmentation with segments of 0.55 seconds works better, but the percentage of words recognized is always less than 35%. That is, however, an interesting result if we think that as a segmentation technique, we have simply used a fixed length for the segments. Okay, so in conclusion, in this paper, we focused on inferring private information measuring the accelerometer vibration caused by speech reproduced on the device itself. We have proposed both an approach for recognizing single letters, digits, in Italian language based on deep learning methods, and a very preliminary generalization to words based on the recognition of syllables. The future works, we will expand set of the syllables to include all the syllables in a given language, and we will try to recognize words in real conversation by studying obviously better ways to perform the segmentation. For example, dynamic adaptive approach or evolutionary methods. This concludes my presentation. Thank you.
Thank you, Rocco. I didn't receive any question. I have indeed a very, very quick question. I think that your results are interesting, but it seems a little bit, let's say, preliminary to some extent. Okay.
Yes.
Do you have the perception that how far, let's say, are you with the future work you are trying to apply, or maybe you are just applying right now to enhance that 35%? To, let's say, something which is more than 50% at least, could be a reasonable trade-off.
Yes, yes. Okay, this is obviously in this paper we have reported only the preliminary results, but we are working actually in other solutions, especially in the we have observed that evolutionary methods seems to give the better results. As an example, genetic algorithms that automatically segment the sequences, the accelerometer measurements by considering, as an example, special portion of the measurements. For example, the silence, that means the passage from a word to another word. So, the method seems to be the best way.
Okay, thanks a lot. I don't have any other question, and I see no other questions right now. So I think we can conclude here this session on mobile security. I would like to really thank a lot all the presenters for the very interesting speeches, and I hope all of you can enjoy the remaining parts tomorrow of ITASEC 2021. Bye, and have a good evening, all of you.